Hi everyone. Today's class is going to focus on density. Now, density is probably a measurement that you've heard of before. I know that you've definitely gone over density in either seventh or eighth grade science. You might have even done it in elementary school as part of a little project that you were working on. So today's focus is on density. Up here, what I put was at the top, very top here, I wrote what is density, and then I gave you the textbook definition of density. So it says the mass of a substance per unit of volume. Now, I have two examples here. In the left example, I have object A, or what I'm calling object A. Object A has a mass of 324.16 grams and a volume of 100 milliliters. Now, I have a second object, which I'm calling object B. Object B has the exact same mass. So again, I have 324.16 grams, but the volume of object B is actually half of what the volume of object A is. So my question that I'm posing to you is, which object is more dense? So if you think about that for a second, if both objects have the exact same mass, I mean to the 100th of a gram, but yet the object B has half the volume, that must mean object B is the one that's more dense. Same amount of mass, packed into 1/2 of the volume. So to answer this question, which object is more dense? It's object B. Same mass in half the amount of volume. All right, so I wrote up here, why is density important? So I wrote, density is a physical property. So again, I'm going to try and tie in all of these pieces that we learned earlier in the year. So a physical property, again, is a property that we can observe without changing the substance. So it's a physical property. It is easily observed. It is widely used to identify pure substances. So one of the tasks that you're going to do for me is a density lab. And as part of the density lab, you're going to be identifying what the density is for these different objects, 15 different objects. And you're going to use the density in order to characterize them. You can also use density to estimate the composition of some mixtures. There's actually a question about this in the density lab that you're going to do as an example. So in order to measure density, you need two pieces. So you need a balance and you need a graduated cylinder. The other way to measure density would be with a balance and a ruler. And the lab that we're going to do is actually going to utilize both of those. So in the lab, we're actually going to measure volume in two different ways. The first way is with a graduated cylinder, and we're going to measure by displacement. So what does that mean? If I have a graduated cylinder, and I'll do my best artwork here, and I know some of you are cringing right now because I'm a terrible artist. So let's hypothetically say that we put water into this graduated cylinder and we fill it up to a volume of 25.0 milliliters. Now, if I take an object, so let's say I take a cylinder, that's what we're going to be using in the lab. If I take a cylinder and I add that cylinder to the graduated cylinder, so this is just a, let's say, metal or plastic cylinder. This is a graduated cylinder, that's the actual name for it. Graduated because it has markings on it that allow you to determine what the volume is. So if I take that object and I lower it down into my graduated cylinder with the water, what's going to happen to the water level? Hopefully you're going to realize that the water level is going to go up. Imagine filling up your bathtub all the way up to the top. When you climb into the bathtub, water is going to spill over the top because your body is displacing water that was in the bathtub. In this case, I have a graduated cylinder with water in it. I'm adding an object to that. That is going to raise the volume of water in the graduated cylinder. So let's say that when we drop the object in, the water goes up to here. I'm just going to show what my object looks like in here now. No, it's not exactly museum quality here, but let's say our volume goes up to 40 milliliters. That means the volume of the object that I put into the graduated cylinder was 15 milliliters. 40 milliliters where it ends up minus the 25 that were in there initially. The only thing that I dropped in was the object. So the difference between the two of those is the volume of the object. Okay, so that's one way to measure volume. The second way is using a ruler. Now, why would we have to use a ruler to measure the volume of an object instead of using water displacement and a graduated cylinder? Well, there's two reasons, two possible causes for this. So the first is if we have an object that won't fit into the graduated cylinder, a giant rock or just something that's bigger than the mouth of the graduated cylinder. We can get larger graduated cylinders, but eventually we might have objects that are too big, like a cinder block. There's no graduated cylinder that's going to be wide enough to fit that. So we have to measure the volume using a ruler or meter stick, whatever the case might be. The second reason why we might have to use something other than a graduated cylinder and water displacement is if that object floats. And this is actually the problem that we're going to encounter when we do the density lab. So imagine for a second, let's take this object back out. Let's get rid of this. Let's say that our water level is back down here at 25. So if we put in a cylinder that floats, that means once it goes in, the water level is going to go up by a little bit. And we're going to wind up with a scenario like this. Part of the object is going to be beneath the surface of the water. Part of the object is going to be above the water. Now, yes, did the water go up? It absolutely did. Let's say, hypothetically, it went up to 30.0 milliliters. The problem is there's a portion of this object that is up above the surface of the water that the water is not accounting for. So in those cases, we cannot measure volume using water displacement. So if our object floats, water displacement doesn't work as a way to measure volume. So instead, in this case, and in the case of the lab, we're going to use an equation. In the lab, we're going to use cylinders. So the equation that we would use in order to measure the volume, so I'm going to put that up here, if your object floats, you're going to use volume equals pi r squared h. You're going to use volume equals pi r squared h. In the lab, you are going to have to measure the h, the height of that cylinder, and you're going to have to measure the diameter of the cylinder. So the reason why you measure the diameter is because it's too hard to measure the radius. Remember, the radius would be from the center of the cylinder to the outside edge. But if you have no way of gauging where the center of the cylinder is, you're not going to get a very accurate measurement. So instead, in the lab, it has you measure the diameter, the distance across the widest part of the cylinder, and then you're going to take that value that you get for diameter and divide that in half. Okay. Hopefully we're good on that. Let's go on to the next slide. Okay, on this next slide, we're going to take a look at just some common materials and kind of make sense of their densities. So if you notice the first two, air and helium, if I take a balloon and I just blow it up myself, I'm using air and basically air that I breathe back out, so might be slightly higher levels of carbon dioxide than in the general air. But regardless, that balloon's going to sink, and that's because the combination of the air inside the balloon that I breathed out and the material that the balloon is made of, it's going to cause the balloon to sink. It's going to fall on the floor. So how do we get balloons to stay up really nice? We fill them with helium. Notice that the density of helium is much less than the density of air. So I have 0.0001. Here I have 0.001. I have almost a greater than a factor of 10 difference. So helium is actually much less dense than air, which is why helium balloons float. We look at the next two here. I have water and ice. So obviously water and ice are made up of the same molecules, H2O. However, in that solid form, hydrogen bonding forces those molecules further apart. This is pretty unique. Most things in a solid form are actually more compact, but water is not one of those. So if you notice, the density of water is 0.93, compared to the density of water, or density of ice rather, is 0.93 compared to the density of water, which is 1.00. Finally, if you look at these last four, I just picked a couple of different materials. So aluminum, you're actually going to see in the lab, that has a density of 2.7, much greater than anything up here. So if you take something that's made of aluminum, it's actually going to sink in water. Lead, also one of the more dense materials on the periodic table, much more dense than aluminum, 11.3. Then if you notice things that float, so imagine you see a log floating in a river. Well, that's because the density of wood is much less than the density of water. So wood floats on water. And then sand, of course, if you've ever poured a bucket of sand, you'll notice, like if you scoop up sand and water at the beach, sand will settle to the bottom. That's because sand has a density that's much greater than water, even salt water. Okay, let's take a look at the next slide. So this slide is called How Do We Calculate Density? And up at the top here I wrote, density is equal to the mass of a substance in grams divided by the volume of the substance in cubic centimeters, or as we learned last week when we were talking about metric conversions, milliliters. Centimeters cubed and milliliters are equal to each other, so you can use them interchangeably. Typically, we use milliliters when we measure volume by water displacement, and we'll use centimeters cubed when we measure volume using a ruler. So here's our equation. This has the units in there, so I have grams per centimeter cubed. I have grams and centimeters cubed here. And then sometimes I just like to write, and this is what I did in the lab, just a simplified version of the equation. So density equals mass divided by volume, or mass, or m divided by v. So now what I wanted to do was to take a look at a few example problems. So the first example problem is this one. We have the mass of a small strip of lead. So mass of lead is equal to 1842.50 grams. If the volume of that piece of lead is 163.05, so volume is equal to 163.05 centimeters cubed, what is the density? So we're looking for density. So on the previous page, we said density is equal to mass divided by volume. So now I can plug in my values. 1842.50 grams over 163.05 centimeters cubed. And I wind up with a density value equal to, so let's take a look at this, 11 point, we have a whole bunch of decimals here, so 11.300214666, and that has units of grams per centimeter cubed. Now, if you think back to the other material that we've learned this year, we talked about significant figures. So we can't leave the answer like this. We have to report it to the correct number of significant figures. So if we look at this number up top, 1842.50, give you a second there. That has how many significant figures? Hopefully we're saying 6. And this number, 163.05, how many significant figures does that have? Hopefully you said 5. So we go with whichever one has fewer or less significant figures. So in our final answer, we're going to be allowed to keep 5 significant figures. So 1, 2, 3, 4, 5. This is the last one that I can keep. I look behind it. It's just a 2. So my final answer is going to be 11.300 grams over centimeters cubed. Okay, let's take a look at the next problem. Before we get to the next problem, what I wanted to do was to just take a minute and make sure that we are able to rearrange equations for a specific variable. So if you look here, I wrote, what if we are given the density and asked to find mass or volume? So the equation that we're going to use is going to be different than the one that we start with. So this is density equals mass over volume. This is asking, what if I were looking for mass instead? So mass is equal to. So when you're solving an equation like this, what you want to do is isolate mass, get mass by itself. So if it's isolated correctly, it should be on top of a fraction, which it is to begin with, and it should be by itself, which means we have to get rid of volume. So volume is actually going to move across the equal sign up here next to density. So we're going to get density times volume. If your math teacher would see this, he or she would say, put volume on this side and this side. Well, on the right side, volumes would drop out and you'd get volume times density equals mass. Same idea. This one is a little bit tougher for most students. So in this case, we're solving for volume. Volume is on the bottom in the denominator. So just moving mass away from it is not going to work. So instead, we have to do the same thing that we started by doing up here, multiply by volume on both sides. So we get volume over here, volume over here. On the right side, it crosses out. So now I have that equation, mass equals density times volume. And now to solve for volume, because that's what we're looking for, we're going to divide by density on both sides. So we wind up with a final equation, volume equals mass divided by density. Again, believe it or not, this is by far one of the biggest hang-ups that students have when we start doing equations. We'll see this a lot when we get to the unit on gas laws, where we have to rearrange equations for a single variable, and students sometimes get mixed up. So keep in mind, another way to look at this, if this is easier, remember the two criteria. It has to be on top and it has to be by itself. So if I'm solving for volume, I can move something directly across the equal sign. So I can move volume over here. I can move density down here because it's diagonal across the equal sign. So if I do that, let me get rid of density here and volume here. If I do that, I wind up with the same equation. It has the same effect as multiplying by something on both sides and then dividing it out. If you move something diagonally across the equal sign, as long as whatever you're solving for ends up by itself and on top of the fraction. Okay, we're going to use both of these equations as we finish up our last two example problems. Okay, so for this example, I wrote a sample of copper metal has a volume of 6.50 milliliters. So we have volume equals 6.50 milliliters. If the density of copper metal, is 8.96 grams per centimeter cubed, what is the mass? So we're looking for mass. So we're going to use our equation, mass equals density times volume. I have my density as 8.96 grams over centimeters cubed. And I have my volume as 6.50 milliliters. Some of you are saying, wait, there's a problem, right? We have two different units. We have centimeters cubed for volume here, and we have milliliters. Remember what we learned on the metric conversion homework. 1 milliliter is equal to 1 centimeter cubed. So I can change my unit of milliliters directly to centimeters cubed. I'm going to type this into the calculator. When I do, I get an answer of 58.24. That is my answer in grams. Now, notice up here, I have 3 significant figures, 1, 2, 3, or 1, 2, 3 really. And for my 8.96, I have 3 significant figures. So my answer can have 3 significant figures. That's an answer of 58.2 grams. All right, we're going to try one more problem together. Okay, so here is our final example problem. It says a cylinder of aluminum metal has a mass of 428.27 grams. So my mass is equal to 428.27 grams. If the density of aluminum, so they're giving us density, is equal to 2.7 grams per centimeter cubed, what is the volume of aluminum in that cylinder? So we're looking for volume. We have an equation that we solved for volume. So volume is equal to mass divided by density. Now, for the next part, what we're going to do, we're going to plug in our 2 values. So our mass, 428.27 grams. And our density, 2.7 grams per centimeter cubed. Notice that our unit of grams will drop out. So we get an answer for this one, a volume of 158.6185185. That is a lot of numbers, and we cannot possibly keep them all. So what we're going to do, let's take a look at significant figures. So up here, I have 5 significant figures, 428.27. For the 2.7, I have just 2 significant figures. And remember that we go with whichever one is less. So we're only allowed to keep in our answer 2 significant figures. So what is this answer going to be when I round it to 2 significant figures? So let's take a look at that. So we're allowed to keep the 1, and we're allowed to keep this place. So we're going to take this. This is going to be the last one that we're allowed to keep. Look behind it. It's an 8, so it rounds up. So be careful. Some of us are going to want to say that the answer is 16, but it's not. So it's 160 centimeters cubed. This 5 is in the tens place. So we have ones, tens, hundreds. So if the 5 is in the tens place and it rounds to a 6, then we have a 6 in the tens place. So it has to be 160, not 16. Don't just chop off the rest of it. Okay. So that does it for the example problems. So we're going to do 2 things with density. So we're going to have a homework. My cyber students are going to have a homework on density, and then we're going to have a lab on density. And those will be our 2 of our 3 tasks for this week. So we've already done some dimensional analysis, and we're going to finish out this unit by looking at density. And then next week we'll do a review, and we'll take our first Unit 1 exam. Thanks everyone.